So good morning one and all. So today we start with a new topic, that is sigmoid neuron. So previously we have dealt with Michel's-Spitz neuron as well as perceptron. Now we'll see something called sigmoid neuron. So before that, for the perceptron we have given inputs, correct? So x1, x2, so on xn. Okay, and finally we got output y. Okay, now so on xn. Now generally, so we have taken all these inputs generally a binary or a boolean, x1, x2, xn boolean. So we got output, it is also mostly boolean. Boolean means which produces either 0 or 1. Now this is the x, input x. It contains some parameters x1, x2, so on xn. Output is only one output, y. This is the perceptron model. Okay. So sometimes you have taken this x1, x2, xn to be real, but output is always a boolean, either 0 or 1. Okay. So suppose if I take all the inputs are real as well as output also real. This input and which leads to an output y, it belongs to a real value. x1 belongs to a real value. x2 belongs to a real value. A real number need not be exactly 0 and 1. So on. So this is x. Okay. X as n features. Okay. Now this belongs to r power n. Okay. So simply in the sigmoid neuron, all the features of the vector x can be real and outputs can also be real. It need not be a binary decision where output is either 0 or 1. Now here output can be any real value. Okay. Now that is what is sigmoid neuron. So now, here where x belongs to r power n instead of 0 to 1 whole power n and y belongs to r instead of 0 and 1. Okay. So here what happened? Each and every feature of this vector x is a boolean, then obviously the vector capital X belongs to 0 to 1 whole power n. Everything is boolean. Output is also boolean. But here in sigmoid neuron, every feature of a vector x can be a real value as well as output can also be a real value. So the vector x belongs to r power n. Why r power n? Because n features of this vector x. What are the x0? X0 is anyway always 1. That is by default. x1, x2, so on xn. Okay. Now that is about sigmoid neuron, where we deal with real numbers. Not only boolean values, we can deal with real values for the input features as well as output value. Now, so recall that a perceptron will fire if the weighted sum of its inputs is greater than or equal to threshold. That is the logic of the perceptron neuron. What happens? So the weighted sum of inputs is more than or equal to threshold. So always remember minus omega naught equal to theta, where theta is a threshold. Okay, theta equal to minus omega naught. So when does the perceptron will fire? When the weighted sum. So let me write here, I equal to 1 to n omega I xi is more than or equal to theta. Then the neuron will fire. Fire means output is 1. If it is less than theta output, the neuron will not fire, output is 0. That is the perceptron rule. It is very, very important. Okay. Now, so let us see what is the problem with perceptron. Okay. So let us go to the movie example, whether we like a movie or not. Okay, so what I have done there, I have taken some features of the vector x. Okay, if you remember properly, I have taken some features of each and every movie. So let me take x1, x2, x3, x4, something like that. Okay, x3, x4, so on, so on. Finally, the output is y. Now, so x1 can be a actor, x2 can be a director. So rating, x4 can be genre, something like that. So we have some features for the vector x. This is vector capital X. Okay, so based on these feature vectors, suppose the movie of your favorite actor means 1, director is not favorite, your favorite director, rating is any value, let us take 0.3, genre is thriller, yes. Now, so finally, based on these feature vectors or features, we take decision whether you like a movie or not. Okay, you go to another movie, so it has got some values, something like this. If all are ones, you may take yes. So suppose the values may be something like this. You may say no, you don't like the movie, you dislike the movie, something like that. Okay, now consider that we base our decision only on one input. Yeah, that is critics rating. Okay, so for simplicity, I am taking only decision based on only one input, that is rating. Based on this one input, I am taking the decision. For example, it is for time being. Okay, now always the rating is between 0 and 1. Let me take always the rating of a movie is between 0 and 1. So based on that rating, we are taking the decision. Okay. Now this is the only one input, that is critics rating x1. Okay, and weight is 1, and here I am taking bias as minus 0.5. So omega naught is minus 0.5, but what is theta equal to? Threshold is 0.5. Is it okay? Is it clear? So for simplicity, I am only taking one input for the making the decision about the movie. Okay, so here I have written so many features of a movie, but let me take only one feature, that is critics ratings of a movie, which always between 0 and 1. Now here what happens? Obviously, what is the logic now? So whenever x1, so what I weighted sum x1 into 1 x1. So whenever x1 is more than or equal to 0.5, output is 1. Simple logic, because we have only one input. Okay, when x1 is less than 0.5, you say that you don't like the movie. Okay, so here based upon this x3, we take a decision whether you like a movie or not. So here the threshold is very simple. So if the input x1 is more than or equal to threshold 0.5, you like it, you say that I like the movie. Okay, so if the input is less than 0.5, you say that you dislike the movie, you don't like the movie. So that is the, so here what I want to say is this is the harsh rule. What I want to say is this is very harsh. So the threshold logic used by perception is very, very harsh. Why it is very harsh? Okay, let me take a simple logic. Suppose if the rating is 0.51, what will happen? It is more than 0.5. You say that I like a movie. Okay, if the rating is 0.59, okay. So if x1 is 0.59, so if x1 is 0.59, the rating of the movie is 0.51, you say that you like the movie. But if it is just below 0.5, that is 0.49, you say that you don't like the movie. Okay, So you take a drastic decision. Okay, what is the difference in the rating of a movie? Very, very small. For the small change in the rating of a movie, you take a very complete different decision. Why? Okay, so the perceptron is taking harsh decisions, drastically opposite decision. But suppose if you ask me, suppose I have two movies with a rating 0.51 and 0.49. I would have said that both movies are okay to me. I would have said I like both movies because the difference is very, very small. But your perceptron is taking very drastic decision of saying a movie with a rating 0.51 is a good movie, with a 0.49 is a bad movie, or you like this movie or you don't like this movie. Okay, it is not good, right? So decision for a movie with critics rating like and dislike. Okay, so it is because of the characteristics of a perceptron itself behaves like a step function. The perceptron characteristics function behaves like a step function. So not only for a movie example, you take any example. Okay, so the perceptron behaves like a step function. It takes a drastic decision around its threshold. How? Like this. Okay, this is a bias. Okay, so it behaves like a step function. If this is input x, okay, around this minus w naught, around is bias. So before bias, just before bias, the output is 0. Just above bias, the output is 1. It is like a step function. You got my point? So there is a sudden change in the decision from 0 to 1 when the weighted sum crosses the threshold minus omega naught. There is a sudden change in the decision of a perceptron when the weighted sum crosses. What is the weighted sum? Take z. Here z is w1 x1 plus w2 x2, so on so on. Whenever the weighted sum z crosses this bias, the output changes from where to where? 0 to 1. There is sudden change in the decision of the perceptron. So for most real world applications, we would expect a smoother decision function which gradually changes from 0 to 1. For most of our applications, we want to have a smooth transition of the decision from 0 to 1, not the sudden change. Is it okay? How smooth? Something like this. We want to have a decision something like this. Something like this. Not the sudden transition or sudden change in the decision. Okay. Now, so now this is called sigmoid. This is sigmoid. So introducing a sigmoid neuron where the output function is smooth, much smoother than the step function. Okay. So we will have a smooth transition, smooth change of decision from 0 to 1, not the sudden change, just like a step function. I hope you know this is step function, right? This step function, right? Now, so sigmoid is a family of functions like this. Sigmoid means generally y equal to 1 by 1 plus e power minus x. The sigmoid function. So in the sigmoid, we deal with logistic function. So in sigmoid, there are so many varieties of functions, but now for time being, we deal with a logistic function which is of this form. 1 by 1 plus e power minus x. So it is in the shape of S shape, letter S. It is something like letter S. Okay. The alphabet S. Clear? Now it is called a logistic function. Now how it is? The logistic function is something like this. The red color curve. This is a logistic function which is a family of sigmoid function. Please remember, which is in the alphabet S. Now, as I told you here, what is that function? Y equal to 1 by 1 plus e power minus omega naught plus summation omega I xi. Okay, so you don't confuse with this. So what is this omega naught plus summation omega I xi? This is nothing but omega transpose into x or omega dot x. Okay, so already we discussed these things. So I can say the sigmoid function, the logistic function that we are using right now is 1 by 1 plus e power minus omega transpose into x, or you can also write instead of omega transpose into x, you can also write omega dot x, double dot x. What are these functions? W, and W is a function as a vector from W naught, W1, so on, Wn, where W naught is called bias. It equal to minus theta. What is theta? A thresholding logic or threshold parameter. What is x? Is an input feature vector. X naught is always equal to 1, x1, so on, xn. Right? Now the logistic function that we are using in our case is 1 by 1 plus e power minus W transpose into x or W dot x, dot product of two vectors. Right? Now obviously, so from this logic, so suppose if the W transpose x is infinity, if it is tends to infinity, what would happen? What is the logic y? What is the y value? What is y value? Y is 1 by 1 plus e power minus W transpose into x. If this is infinity, what would happen? 1 by 1 plus e power minus infinity. So e power minus infinity tends to 0. This is 1. Obviously, if W transpose x tends to minus infinity, what is the output y? Equal to 1 by 1 plus e power infinity. So e power infinity is anyway infinity. 1 by infinity is 0. That is what same thing is happening. So whenever this W transpose x tends to infinity, what is this value tending to? 1. Whenever this is minus infinity, what is the value of this? 0. Is it okay? Now, so whenever W transpose x equal to 0, when this is 0, what will happen? What will happen? When W transpose x equal to 0, y equal to 1 by 1 plus e power 0. E power 0 is also 1 by 2. Okay. So what would happen here? Whenever it is 0, somewhere here, let us take. So whenever it is, sorry. So W transpose x equal to 0. Otherwise, you can say that W naught plus summation. What is W transpose x? Actually, W naught plus summation I equal to 1 to n double I xi equal to 0. Okay. So what is this quantity? Equal to minus W naught I equal to 1 to n double I xi equal to minus W naught. So when that sum is minus W naught, what is the value? 1 by 2, somewhere here. At minus W naught, the value is 1 by 2. So otherwise you go to this equation here. When this quantity is equal to minus W naught, what would happen? So e power 0. E power 0 means 1. 1 by 1 plus 1 is 1 by 2. Okay. Now, so from this figure, you can say that the logistic function always lies between 0 and 1. It can be real. It can be any value between 0 and 1. The logic is, so the logistic function can be any real value between 0 and 1. Is it okay? It is something like this, right? So it can be any value between 0 and 1. Okay. It is something like, can you tell me any parameter which is always between 0 and 1? Probability. Okay. So using this logistic sigmoid neuron, we don't give you the binary decision of like or dislike. Instead of that, we'll give you a probability of liking. Is it okay? So here I told you, in case of logistic function, output need not be always 0 or 1. It can be any value between 0 and 1. Suppose, yeah, it can be somewhere here. The value may be this value. The value may be here. It may be here. It may be here. It is a continuous function. So you may get any value, any real value between 0 and 1. Which means it is something like giving a probability of liking the movie. Not simply saying I like, I don't like. Okay. So we don't give some harsh decisions or drastic decisions. So instead of like or dislike decision, we get a probability of liking the movie. So here you may get something like this. So here what will happen here? So in case of Perceptron, based on the critics rating, you are giving a decision of either 0 or 1. But here in logistic case, what I want to say is output is, suppose if the rating is 0.51, what would I say? 51% I like the movie. Okay, a simple example. Suppose if the rating is 0.49, what would I say? I won't say I won't like the movie. What would I say? I would say 49% I like the movie. I am giving the probability of liking. Is it okay? So instead of saying I like, I don't like, which is a sudden change in the decision, what I would say is, so 51% I like the movie or 49% like the movie. Now you can say that there is no change in the behavior of the human beings. It is just like our humans. Okay. So if I ask same question to you, you would have told me same thing. So I don't expect that nobody would say that a movie with rating of this much difference will take the drastic decisions. Like here I say movie is good, here I say movie is bad. No one will say that. Instead we say that both are okay. So this is what we expect. Okay. So here the sigmoid neuron will give you a value of output which is a real number between 0 and 1. It is just like probability. Okay. It is not a binary decision of saying like or dislike or 0 or 1. Okay. Yeah. So what is the difference here? So we only deal with weighted sum. Y equal to 1 if the weighted sum I equal to 0 to n omega I xi is greater than equal to 0. Okay. So output is 0 if it is reverse. But here, so this is what the perceptron, this is the sigmoid or logistic neuron. Here what is this? This is a logistic function. Now y is a real value between 0 and 1. The only difference is here y can be either 0 or 1. Only two possibilities, either 1 or 0. But here y can be any value between, okay, any real value between 0 and 1. It is just like the probability. Okay. Now here this sigma is called sigmoid neuron. The sigma indicates sigmoid neuron. Okay. Now how to calculate the sigma, we will see now. Okay. Now the basic difference is the nature of the output. Now everything is same except the nature of the output. Okay. Most of the times we would expect output to be smooth, not the harsh or sudden change in the output. Okay. Now the perceptron is not smooth and not continuous at minus omega naught. It is not continuous, it is a discontinuous and not differentiable. Okay. Now whereas sigmoid neuron is a smooth, continuous and differentiable. Is it okay? You find a difference between these two. Right. Next. Okay. So we'll say something like a supervised machine learning setup. Okay. So earlier we have seen this thing. What you have seen? So we have seen that this is the setup where what is this setup? This is not linearly separable. Why? Why? Because we have some outliers, some misclassified points. Okay. Now, earlier we have mentioned that a single perceptron cannot deal with this data. Why? Because as I told you, this is not linearly separable. It misclassifies 3 blue points and 3 red points, but we could live with it in most of the real world applications. Okay. What I want to say is, yes, it is misclassifying 3 red points and 3 blue points, but we are okay with it. We can live with this because in most of the real world applications we can deal with this type of errors. We are getting maybe 30 out of 10. Here also we are getting 30 out of 10. Some points are misclassified, so here the error is minimum. Most of the points are classified properly, but some points are misclassified, which are very, very small in number. Okay. So in most of the real world application, we can live with these errors, which are very, very minimum, bare minimum errors. Okay. Because it is very hard to get zero errors. It is very hard or difficult to get zero errors. Okay. The only thing is we can look for minimum errors instead of zero errors. It is something like ideal case. In ideal case, you may get zero errors, but in most of the cases, you may get some errors. But in most of the applications, we can live with these errors. Okay, except some medical applications where there would be a life and death situation. There you might need zero errors. Except few applications, in most of the application, we can live with these minimum errors. Okay, we don't have any problem with these errors. So from now on, we will accept that it is hard to drive the error to zero in most cases, and will instead aim to reach minimum possible error. Okay, so forget about zero errors. Our aim is to get minimum errors, minimum possible errors. Always try for minimum errors. Okay, instead of zero errors, try for minimum errors, because in most of the real world applications, we can live with the minimum errors. Okay. Now, so obviously, so this is data. Xi is a movie, yi is a like or dislike. Now let me go back to that data movie example only again, as I told you. Yeah. Here, so xi, some xi. Xi is a movie, yi is the decision. Whether you like it or not, whatever it is, decision. Okay. Now, so we have data. This is data, complete data. Okay. So data xi by I varies from 1 to n. Okay. For each and every movie, we have some features. So based on those features, we take decision. Right. Now, so there is a true relation between this y and x. Okay, so which is not known to us. Okay, so listen carefully. There is a relation between y and x, a true relation which is not known to us. Okay, so you may like some movies, you may not like some movies. Okay, so the reason is not known to everyone, but there is a true relation between this x's and this y, which is not known to everyone. Is it okay? There is a true relation between the decision and the inputs. Okay. Now, but we assume that y is a function of x and w. Y is a function of x and w. Okay. Assumption. I assume that there is a relation between. This is my assumption. Please remember. Actually, what is the true value? Y equal to f of x. We don't know what is that relation between x and y. So, I assume that this is a prediction. F is a function of x and w. Is it okay? Listen carefully. What is x? Data. The data that you give. What is w? Weights. Weights associated with data. Is it okay? Now it could be something like this. Suppose if it is linear, so y bar could be wx plus b. Something like this. This can be a relation between y and x. But there is a true relation which is not known to us. So we are assuming some relation between y and x. Now here w is a parameter which is need to be taken care of. Is it okay? Here I have taken a data x1, x2, x3, x4 and y. Okay, for each and every row there is a features as well as y, which is a decision value. Now, so here now in our sigmoid neuron we assume this relation between y and x. This is our approximation of relation between x and y. Is it okay? Now, so here I am approximating y with a relation between x and y. What is that? 1 by 1 plus e power minus w transpose into x. Please remember. This is only approximation relation between y and x. But, so what is a parameter which need to be learned? W. Because x is data which is given to you. So y will be the output. Y cap will be the predicted value. So we have to learn these weights. Okay. Now obviously for learning weights, we go for algorithm. Already we have discussed Perceptron learning algorithm, where we have learned the weights. How? Based upon errors. If you remember properly. So for case 1, we have updated the weights w equal to w plus x. For case 2, W equal to W minus X. This is called learning weights. Is it clear? Okay. So this is called Perceptron learning algorithm. Now here we deal with some other algorithm where we learn weights. What is the aim? Our aim is this y cap should be approximately equal to y. So this prediction should be same as the true value. Remember, this is a prediction. This is a true value. Okay. So our aim is to make a predicted value is close to the true value so that we get minimum errors. Okay. For that we need to update these weights properly. Is it okay? Okay. Now objective loss error function. Obviously there can be some errors. Is it okay? What happened? Suppose this is a true value. This is a predicted value. Y cap. True value, predicted value. So what is the error or loss function? It's very, very important. It is called loss or error function or objective function. What is that? So what is error actually? It is the difference between these two. You take any value. Y cap minus yi. But we take square of the errors. What do we say? We say that summation I equal to 1 to n yi minus yi cap whole square. Please remember, we take square of the errors. Always we take square of the error or loss. Okay. Why we take square? See, suppose, so it may happen that sometimes error can be, let us say, positive 0.5. Sometimes error can be negative. Then what happens? So ultimately, if you don't take square, sometimes it may give some false assumption that there are no errors. Okay. So to overcome these negative errors, we take the square. If you take square, all are positive errors. Is it okay? So if you don't take the squares, the positive errors may cancel with the negative errors, which will give a false impression that there are no errors. But that is not true. Okay. So to overcome that, we take square of the error, sum of squares of errors. This is called loss function. So if you minimize the loss function, obviously these two will be approximately equal to each other. If they equal to each other, there will be minimum errors. How it is possible? By choosing proper values for the weights. We have learned the weights properly. Is it okay? So please remember, this is the square of errors, sum of squares of errors. Okay, one more thing is, okay, so here we are assuming omega naught to be equal to b. What is omega naught? Omega naught is a bias, that is minus theta equal to b. So simply we are assuming omega naught equal to b. So in our case, generally, what you written? So if you think properly, omega naught plus summation I equal to 1 to n omega I xi. This is equal to what? Actually, that is equal to omega transpose into x. That is also equal to omega dot x. Is it okay? So don't get confused here. It can also be written as summation I equal to 0 to n omega I xi. Is it okay? If I write from 1 to n, I am writing from 1 to n. If I write 1 to n, what is omega naught into x naught? X naught is always 1. Omega naught into x naught, right? It is always 1. So we are left with W naught. So that's why this is also one way of writing. Okay. Suppose this is b. Then what is the final weighted sum would be summation I equal to 1 to n omega I xi plus b. Okay, or so if you take omega as w or omega, you can call w1 so on wn, and if x equal to x1 so on xn. Now what is this above quantity? What is this quantity now? This quantity is only this quantity. What is this quantity will be? Obviously w transpose into x or w dot x. Please remember. So finally the weighted sum can be b plus w transpose into x, or you can also say b plus w dot x. Okay. Now this is what the y cap, that is called f of x. Okay, before that okay, right. So yeah, we stop here. We'll discuss about that Sigmoid neuron in the next class.